Okay, in this section, we're going to be talking about max and min values of two variable functions. Start with anyway. Z equals f of xy. Okay, well, as we recall, from one variable functions, y equals f of x functions, we talked about local mins and maxes, right? If you have a local max at C, an x value C, if what? If f of C is greater than or equal to f of x when x is near C. And a local min, yeah. A local min, flip the inequality. F of C is less than or equal to f of x when all those x values are near C. Well, when you do two variables, z equals f of xy, it's very analogous. You have a local max at, now, the thing is, you're not just talking about a particular x value, you're talking about a xy point, right? So you have a local max at, and they use the a, b for the point. If, but it's the same idea, f of ab is greater than or equal to f of xy, for all points xy in a region around AB. Okay. Yeah, the minimum is very much analogous there. But yeah, so, you know, here we're talking about just x values near C, so you're just talking about a little bit of a, you know, number line. You're looking at these values. You have a max, you're looking at this C value, and so you're looking at the x values around that C value. Well, when you go to two variables, you got to think about a region around a particular xy value, not just, you know, an x part or y part. It's in conjunction. So you're looking at a region around. So here's your surface. Let's say. Yeah. So you got to look at from points all around it. So it's kind of a blob around it, as long as that particular function value is bigger than all the function values around it. So you're kind of looking more in three dimensions in that particular case. All right. Okay. Yeah, and so the local min is very much analogous, less than or equal to in that particular case. All right. Now, also recall where we looked for these local max and min values. Remember what we looked for? We looked at the critical values. And critical values, tangent line horizontal, okay. F prime of C equals 0, or we also could have F prime of C does not exist. Well, it turns out, and that's where you look for local maxes and mins. Well, it turns out that local maxes and mins for your two variable functions, z equals f of x, y, the critical points, you look at the partial derivatives. And it turns out let me just state this. This is the theorem right here that we'll focus or use. If z equals f of xy, two-variable function, if that has a local max or min at the point AB, then the partial derivative with respect to x at AB equals 0, and the partial derivative at y at AB equals 0. So we see kind of the connection there. You got the partial derivative equals 0, and that has to be both. Both of them have to equal 0. Okay? And so that's kind of the critical points we're going to look at, is when the partial derivative of AB equals 0 and the partial derivative with respect to y equals 0. That's going to be where we focus our attention. Okay? Now, just to give you an example here to look at. Say we've got f of xy equals x squared plus y squared minus 2x minus 6y plus 14. Okay, and so we said we want to look for where the two partial derivatives equal 0, right? So what does that translate to here? Well, the partial with respect to x would be 2x minus 2. So we set that equal to 0. And the partial of f with respect to y would be 2y minus 6. So we set that to 0. And so we solve that for x here. Get x is 1. Solve this for y. You get 3. And so the critical point here that we'd want to maybe look at is 1, 3. So our AB, our critical point, if you will, is 1, 3. All right, well, they go ahead and just graph this one just to kind of show you that this does work. And the way they do it is if we complete the square here, you know what I mean? Complete the square. So you add 1 here. And so we subtract 1 to counteract that. And then here we take half of that and square it, so that'd be 9. So we subtract 9 to counteract that. And so we wind up with x minus 1 squared plus y minus 3 squared plus 4 is our function here. And since both of these are these parts are greater than or equal to 0, you can see that the lowest value is 4. And 1, 3, 4 is kind of the vertex, not really. It's the three-dimensional version here, but here's what it looks like. It's a paraboloid that bottoms out here at 1, 3, 4. So this is 1, 3, 4. But you can see there it's definitely a minimum at 1, 3. So at the x is 1, y is 3 value, we do have a local min there. And matter of fact, it is a absolute minimum there. We'll talk about those maybe a little more later on. Okay, but this does give you a technique to look for those values. Now, let me show you this one though, because that theorem I wrote down doesn't guarantee that if you've got the partial with respect to x and the partial with respect to y equals 0, it doesn't guarantee that you have a local max or min. Because look at this one. F of x y equals y squared minus x squared. Well, the partial of x, partial with respect to x is negative 2x. And then the partial with respect to y is 2y. So if we set those equal to 0, our critical point is 0, 0, right? However, let's look at the graph on that one. And this isn't how we'll be doing these, but just to show you what can happen. Turns out, see if I can draw it here. Kind of get this crazy looking shape. Like that, kind of a bowl shape, and then it's got also another, but right here is 0, 0, 0. So we've got our x, y, and z kind of going out like that. Okay, there's our 0, 0, 0. And so if I look at that, put a kind of some more dotted lines in there, you see, is that a relative max? Well, no, because these points over here, it is bowing up a little bit here on either side of the 0, 0, 0 point. So it's not a relative max there because there's points around it that are larger. In the other direction, it's kind of a minimum, but there are points lower than it if you go out this way. So it's kind of a maximum this way, but there are points going along here that are higher. And then it's kind of a maximum in this way, but there are points higher. So there's points lower and points higher than that point. Kind of contradicts it. Okay, yes. So it's not a relative max or min, or local max or min. F of 0, 0. Yeah. Okay, so that's called what's called a saddle point. Saddle point. For good reason, right? Kind of like a saddle. And the book mentioned the on a mountain pass or something. You know, you can maybe it's a crosswalk here. You can walk across it here, but if you're coming in from this direction, you're going up. Okay. So yeah, you got a saddle point.